Okay, so we're starting with sample problem A. Obviously, let's read it. Let's fill in our data table as we go. A water balloon is thrown downward from the top of a tall building with an initial speed of 5 meters per second. What is the displacement of the water balloon, and what is the final velocity of the water balloon when it strikes the ground? What is the one piece of information we always know we should be able to plug into every data table that involves vertical data? Negative 9.8 goes in for G. So let's put it there, negative 9.8. Nick, why don't you go ahead and give us one more piece of information?
For initial velocity 5.
Okay, be careful though. Okay, it is a speed. When you see speed in these problems, we should be cueing into there's something else going on. Where is it thrown?
Downward.
So that has to be as a velocity value needs to be what? Negative 5. So negative 5 here for our VYI. Carly, anything else you'd like to throw out? I'd say there's one more piece of information we can put into our table. Okay, 3 seconds. Okay, so we have that. Okay, so we are asked to solve for the displacement, and we are asked to solve for the final velocity. So we actually have 2 question marks here. We have nothing that's crossed out. But if we're going to solve for the displacement without the final velocity, which one of our kinematic equations are we going to find, or which one are we going to use? Which one are we going to use? Equals VIT plus 1/2 GT squared. Okay, we can try that. Okay, so VIT plus 1/2 GT squared. Well, let's go ahead and let's substitute in since we seem to have everything. So that'd be negative 5 times our value of time of 3 seconds plus 1/2 times negative 9.8 all times 3 squared. Once we have that set up, pluggy chuggy. And Kendall, let me know if you got a good value. Negative 59.1 meters, which, believe it or not, actually is a pretty significant drop. Each floor of a building is approximately 3 meters, so this is going to be a healthy drop. So A, we throw it down with an initial speed, so we're not just going to release it from rest. It's already has some speed in a downward direction. It's going to continue to accelerate downward. And it falls for 3 seconds. It's in free fall for 3 seconds. You found out from your golf ball gravity lab, even just at 1 second, what travels about the 5.4 meters or so that we have from railing height all the way down to the ground. Okay, so for 3 seconds, as it's continually accelerating, it's actually going to fall a pretty great distance. So I know at first that might seem a little odd. It seems large, but it actually is a very accurate value. Now, we have the value of our displacement. We have some options as to how we can find V final. What equation, Jacob, would you like to use?
V final equals V initial plus G initial.
Okay, I would say for this problem, that's perfectly fine. Okay, so V final equals V initial plus GT. Okay, first off, the initial velocity, acceleration due to gravity, and time, they're all knowns in this problem, so it's not like we're going to have any rounding error. I know the 59.1 is an exact value, so we could use that if we really wanted to, but there is an easy way to do it, so why wouldn't we do it the easy way if it's not going to affect our results? Okay, so negative 5 plus negative 9.8 times 3. And by the way, we are making the assumption that at 3 seconds, that's when it strikes the ground, and that's a safe assumption for this problem. Okay, so -5 plus -9.8 times 3. And Jacob, let me know what you got. Quality response.
7.3.
I think we may have forgotten a negative somewhere. Maeve, you want to help out for a minute?
24.4.
I think we're also missing a negative somewhere. Alondra?
Negative 34.4.
That's what I'm getting. -34.4. It is a velocity, so units of meters per second. Okay? Now, for Jacob and Maeve, I'm actually kind of glad, even here, this is our point. We have to make sure that we're getting the negatives. This equation should kick out the negative, and that should be our check for this. We're throwing it downwards. This final velocity should be a negative value as well. And just to kind of put some context to this, I know some of you may have the inkling to say, well, Talbot, after some time, it's going to come to rest because it hits the ground. But when you're asked for the final velocity in these situations, we're looking at the impact velocity. What is the speed that it strikes the ground with? Of course, if we were to leave this water balloon go long enough, yes, the water balloon and all its contents eventually will rest on the ground. Okay, but we're looking for the impact speed, okay, or impact velocity here, which would be -34.4. Jacob and Maeve, when we go back to check it, are we good now? Okay. Okay, it happens. All right, any questions on sample problem A? Pretty easy. I know you probably could have done this if we just would have given it to you right out of the gates, but okay, a good place for us to start. All right, sample problem B. You and a friend are going to toss a coin to determine who asked Mr. Talbot for help, since I guess neither of you really want to ask me for help. Okay? You toss the coin up with an initial velocity of 6 meters per second. We have a couple of things we are going to find. How high does the coin go above the point of release? And what is the total time the coin is in the air before returning to its release point? Alex, give me something to plug into our data table, please.
-9.8 for G.
Good! -9.8 for G. Michaela, something else to add in. Okay, for our initial velocity, I'm okay with us putting it in as 6. Anything else we should put in?
V final is 0.
We need to be careful about it, and I'll explain why. I don't want you to put anything in for V final just yet. We'll see why in a minute. So actually, there is nothing else because we are going to be finding delta y, and we're going to be finding t. So we're asked in our first question, how high does the coin go above the point of release? Now, I want to just draw a very simple diagram for us. So at some height, we're tossing a coin up in the air. It's going to get up to its maximum height. Then it's going to come back down. It's going to return back to the same height. We kind of cued you in a little bit last class. This is what we call a symmetrical problem. And on symmetrical problems, we can manipulate this concept of V final a little bit to help us out. If we were to go ahead and calculate delta y, which I'll tell you we're actually going to use V final and V initial, so we're going to end up using this equation, Vf squared minus Vi squared, all over 2g. If we were to actually use the V final, see if you remember this, because we don't take into account air resistance at this point. What would the V final be if we let this go all the way back to our hand? If we're talking about the impact velocity back in the hand. We launch it up with a velocity of 6, comes back to the same height. What should it be back in your hand? 6. -6. Okay? Now, don't use that though. Because let's take a look at this. V final, if that is -6, what is -6 squared? 36. What is 6 squared? 36. What is 36 minus 36? 0. You have calculated a displacement that should be 0 because we've treated the final displacement based off of the exact same height that we started at. So we have to treat V final differently. But here's the other nice thing about this. When we manipulate that V final, we know one other spot where we know another velocity. Where is that point? At our maximum height. And in all instances, for anything moving vertically, what is the velocity at maximum height? Vertically speaking, it is 0. So we can treat this as 0. So 0 squared minus the initial velocity that we're given, all over 2 times negative 9.8. Please do me a favor and pluggy chuggy exactly as you see it on the board. And Aaron, when you have a good response, let me know.
I got 1.837 meters.
Good. And that's what we should get. Okay? 1.8 meters. That's a healthy coin toss. Remember that each story of a building is approximately 3 meters. I mean, that would be reasonable, maybe a little bit more than about half of that for a coin toss within reason. Okay, so that would be the height that we would get. And I will restate this, and maybe you can write a healthy note to yourself. Anytime you deal with anything at maximum height, we're going to treat that velocity point as 0. So what did we actually do? We didn't really use the whole situation. We went from our starting point up to maximum height. And we used that to calculate the way in which we find the height in this instance. So any instance where we're going up to max height, we should treat that V final as 0. Now, to confuse you a little bit, let's calculate time. For time, do we know the final velocity when it returns back to our hand? It's negative 6. Because if there's no air resistance, since it is a symmetrical problem, okay, the speed it's launched with is going to be the speed it comes back down with. So we can use V final minus V initial all over G. Where we could do negative 6 minus 6 all over negative 9.8, and that would give us the total time. Since we treat our initial point as here as the initial launch velocity, final velocity when we come back down. So, well, that should be a pretty simple calculation. Paige, what do we get? 1.224 seconds, and I would agree with that as a response. Now, understand that we were finding the total time over the entire range of this point being in the air. And here's what I want you to do. Put your pencils down once you kind of have that written. And I want you to go through a little bit of an exercise with me. Since hopefully you have entered everything in one long string, as we should, I would like for you to do the following. Enter into your calculators 0 minus 6, all divided by negative 9.8. 0 minus 6, all in parentheses, divided by negative 9.8. Enter. Now, let's talk about what that calculation just did. That would be the calculation of the time from launch up to maximum height, because we would treat the final velocity as 0. Take that number in your calculator and multiply it by 2. since it is a symmetrical problem, that's another way in which we can approach doing it. But I need to urge you caution. You have to remember to multiply that by 2 on symmetrical problems. Which is why I prefer, on a symmetrical problem, if we know both the initial and the final, which we should, use that for your time calculation because it calculates it all in one step. And typically what happens is the students that do 0 minus and then go ahead with that calculation forget to multiply by 2 for the total time on a symmetrical problem. Now, I needed to do my part to tell you that that's something that we can do. On a symmetrical problem, though, that's what I'm doing. Any questions with either of them? Yes, sir?
You know, it can be like symmetrical like that.
No. That's the next problem that we're going to see is an asymmetrical problem.
How would we?
That's a good question. The question is, how do we know it is a symmetrical problem? It returns to its release point, or release height. Anytime that you have any indication that it's going to return back to the height that it started, it has to be a symmetrical problem.
Because the other question was like something happened that like made it like not symmetrical, like.
Well, we're not quite at that type of example yet. But let's take a look at our next problem, which is going to be an asymmetrical problem when we get to that. Okay? All right. So here we go. Since it was asked, and I do have to say, these asymmetrical problems, typically there's a bunch of things that we need to solve for. Okay, a water balloon is shot up from the top of a building and given an initial velocity of 20 meters per second straight upwards. The building is 50 meters high, and, Kivash, here you go, to kind of answer your question. The balloon just misses the edge of the roof on its way down. So it's not landing at the roof height that it was launched from. Okay, we have a whole bunch of things that we are going to determine. So I'm going to draw just a very simple diagram here. We have a building. We are launching a projectile up. It's going to reach some maximum height, but then it's going to fall all the way back down to ground level. About as asymmetrical as we could make it. It's not even close to returning back to the same height at which it started. So the way in which we approach some of this is going to have to be different. Okay? Here's what I would like for you to do. The VYI, we do know that is our launch velocity of 20 meters per second, and we know G at negative 9.8. I would prefer for you to not fill anything else in on this table. Can we right now do part A, the time at which the water balloon reaches its maximum height? Can we do that?
Yes.
Okay, that's kind of similar to what we just did. And before I let you loose on that, can we also start the calculation of the maximum height?
Yes.
Let's kind of go back to our previous question. What are the two things that we really did here? We calculated the maximum height for something that was launched upwards. And we found the total time. I think we can use that to find the time it gets up to max height. Why don't we start with that, and then we'll see how we do. Okay? Go ahead, take a couple minutes. We'll work through part A, and we'll work through part B. Do not go on to C yet. For the time calculation, yes. Because we're going up to max height. Okay, let's come together for a minute because actually I want to catch you before we're all the way done with B. We should have at least gotten a healthy start on A. What equation do we use to figure out the time up to maximum height? We absolutely should be doing VF minus VI all over G. What do we plug in for V final since we're going up to max height? Okay, 0 minus our initial velocity of 20 all over negative 9.8. Okay, and Emily, when we go ahead and we calculate that, we get a, oh, I'm sorry, I put the wrong letter out in front. Let me correct that. Solving for time. Okay, when we get that time, what do we get? Yeah, we should get something a little bit different than that. That's okay. So just make sure we have the parentheses done properly. Okay, so 0 minus 20 all over the negative 9.8. Who would like to offer a helping hand? We get 2.041 seconds. Okay, would be the time that it takes to get up. Now, if this water balloon had just happened to go back to the roof of this building, we know that it would take 4 seconds in order for it to take the full round trip. Okay? We'll get to the total time in part C, because we have to incorporate everything that we have going on. But in order to do that, we need a little bit of help from what we're doing in part B. So let's kind of scroll to that point. Okay, now we're going to find the maximum height, which we're going to use the same equation as to what we did in the previous problem. It's going to be the VF squared equation rearranged. And again, since we're going up to maximum height, what do we treat V final as? 0 minus 20 squared all over 2 times negative 9.8. Please, I'm still seeing some of you trying to calculate this in chunks. Plug it in as the entire string. Open parentheses, 0 squared minus 20 squared, close parentheses, divided by, open parentheses, 2, open parentheses, negative 9.8, close, close, enter. Okay? Do it all in one fell swoop. And Jacob, when you have a quality answer, as I know you've got, let me know. 20.408 monkeys.
Yeah.
Thank you. Quick question. Is that the height? Maeve says no. What is it, Maeve?
You have to add 50.
Absolutely. Because what is the 20.408?
That's the height from the building.
Good. That is the height from launch point up to maximum height. But since this water balloon is then going to travel all the way down, okay, this 50 meters, all the way back down, that's not the height relative to the lowest possible point. And understand that heights are always measured from the lowest possible point. When you measure your height, we're standing here on the second floor here at Riverside. You don't dig down the floor and then use that as part of your measurement of your height, do you? No. Okay? You go from your lowest possible point up to your tallest point. And that is a simple measurement of height. It is not a displacement. Okay? So we do have to, in this case, add in the 50 meters that we had from the very beginning, which would make that 70.408 meters above the ground. Alex, you had a question, or are you at least holding on? Okay.
On that negative 20.4, really, I have like the same solution.
May have forgotten to divide by negative 9.8
Oh, okay.
because, let's be real, this is 0 minus 400 at top, so it should be negative 400 divided by negative 19.6. So the negatives should cancel out when we go ahead and do that. Yes, sir.
Why wouldn't the other equation work?
Why wouldn't the other equation? What do you mean the other equation?
The other,
Quadratic one.
The VIT?
yeah.
Okay? Because in order to do that at this point, we would have to know the total time.
But if you do time first,
But be careful, what is it the time of? That is only the time from launch up to max height. It is not total time. So technically, Kivash, if we wanted to know this, and I hear what you're saying, I'm trying not to confuse you because there are 14 million ways in which we can dissect this problem. You would need to know, let's put it this way, we know the time up. I know it's kind of a hard way for me to diagram that there. What would you need to get from here to here from a displacement standpoint? Using the VIT equation, we would have to already know the time down to get there, which we don't have at this point.
So like when you use that equation, where do you find that answer?
This, in part B, what we have here.
If you do the quadratic one, so like
All right, I'm going to put the brakes on it. You're not going to use a quadratic here. We'll use it in a second, but not for that purpose. Okay? All right, so now we found the first two things.
I use the VIT equation at that.
You use the VIT equation for this, okay? And you treated your initial velocity as that, and you plugged in that value of time. That could get you there. I just don't think that's a wise idea, because this is how we're going to be calculating heights more often than not. So I'd say for consistency's sake, we should use the VF squared equation. Okay? And that's kind of what I'm saying. There are so many different ways in which we can solve certain components here that I'm trying to give you the most cohesive way to do it. I personally think for what we're asked to find, these are going to be the first two steps that are going to be the easiest to do. Okay, now I need to clear this information so I have enough room so we can do parts C and D. Does everyone have everything written down?
Yeah.
Okay, so let's do this. Okay, real quickly, I'm just going to put our diagram back up. So we have our building, we've launched, we're going back here. All right, so now we're going to find in part C the total time. And as per what we were just discussing, I know that we technically have the time up. One of the things that we could do is we could also separately find the time down and then add the two of those together. That just becomes a real big mess. So we're actually going to rewind, and now we're going to do the quadratic for the total time. Okay, so that rearrange 1/2 GT squared plus VIT minus delta Y when we go ahead and put it into our free fall version of the quadratic. Okay, let's set this up. We kind of talked about it earlier. What is 1/2 of negative 9.8? Negative 4.9 t squared. In this problem, do we have an initial velocity? Yes. What is that initial velocity? 20, so plus 20t. I want you to think very carefully for about 10 seconds before you answer this next question. What is the displacement? What is the displacement? Alex? 90.016. No. Or negative. Isn't it negative 50? Remember, displacement is about where you start and where you finish. Where do we start? At the top of the building. Where do we finish? On ground level. It doesn't matter that we've gone up the additional 20 odd some meters up in the air. In terms of actual displacement, okay, we're going to go ahead and get that as negative 50. So when we subtract a negative 50, that would become plus 50. So here's what we're going to do. We're going to solve for it graphically. Okay, so go into our graph, which we already hopefully have our scale set as the minimum negative 100, positive 100, scale of 10 on both axes. So negative 4.9x squared plus 20x plus 50. Then we can go ahead and calculate the zero. Set your left bound, right bound, and we should be able to get it. Michael, what you got? Okay, 5.831 seconds. is what we should get. Now I know it took about 2 seconds or so to get from our release point up to maximum height. It certainly is going to take a lot longer on the return trip down. For those of us that can do the mental math, that's about 3.8 seconds on the return trip down. We're going to have that disparity between the time up and time down. Now, again, there are, with this part alone, I can teach you 3 or 4 different ways to do it. This is just going to be our easiest way to do it, but we have to remember this is the total displacement. Where do you start? Where do you finish? Any questions with part C? Okay, part D, once we have everything solved, actually should be the easiest. What is the final velocity of the water balloon when it hits the ground? Well, I say let's just go ahead and do it the easiest way. V final equals V initial plus GT. Even with this one, we now have options. But let's just go ahead, let's use the actual initial velocity, and let's use the actual time. So initial velocity was 20 plus negative 9.8, all times the total time of 5.831. I know it's going to have some inherent rounding there as part of it, but I'm fine with that. And Justin Hampton, once you have that, let me know. What's that? Give Justin a chance.
Negative 37.144.
1, 4, 4. Monkeys, bananas, gallons of milk.
Meters per second.
Meters per second. Okay. I know that seems like a healthy velocity in the negative direction, but okay, we're 50 meters off the ground, and it's going to have, you know, some velocity. It's actually falling from a height of 70 odd some meters, because that's the point where it turns around. It's going to have a healthy velocity when it comes back to the ground. Question?
I still have problems with my calculator. I can't figure out the zero. And I still left and right down and it says no sign.
Okay, I'll take a look at that in a second. Okay, question?
So for this one, would we not put anything in the data table for delta y and g?
I wouldn't, because all we really end up using that is consistent across all steps is the initial velocity in g.
Okay.
The table is just for you to organize. I don't grade you on how we do on the table without putting information in there. It's just a way for you to have some organization to the information that's given to you in the problem. If you want to use it, use it. If you don't, it's personal choice. Okay? All right, are we good with this problem? Now, I do need to say, yes, this is a longer problem. It's going to take us a couple of steps. But the good news is, okay, when I'm going to ask you to do these asymmetrical problems, it's going to be the exact same setup and the exact same step. Part A is always going to be the time up to maximum height. Part B is going to be to find the maximum height. Part C is the total time. Part D is the impact velocity when it comes to the ground. So it's going to be the exact same setup and process as to what we did here.